Okay, so hi everyone. It's a pleasure to be here and talking about trying to create an audio software house. My name is Nuno. Vitor is here with me from Sound Particles, and we are. The idea of this session is pretty much to talk and have a session that I would really love to hear from others and see how other people are doing. This is not about the right thing to do. This is pretty much a journey, what we have done, all the pains that we have, especially the growing pains of creating software. And before entering the details, some context. So Sound Particles was created pretty much based on an idea. Like probably 15 years ago, I realized that the most interesting visual effects that I was seeing on movies use particle systems. That is a technique in computer graphics where you generate thousands of points to recreate fire and smoke and desert storms and fairy dusts. And I thought it would be interesting to do the same thing with sound and create thousands of small sounds that together would create fantastic soundscapes. So that was beginning of Sound Particles, and pretty much our initial software that today is still our main software. It's called Sound Particles. So it's imagine a CGI kind of software, but for sound. So each point that you see over there, it's a sound. So you can generate thousands of sounds around you. And then instead of virtual cameras, we have virtual microphones. And the software is pretty much used in movies and TV, especially for epic sound design. So if you want a battlefield with 10,000 sounds, that's how you do it. And the software is used in things like Star Wars, Game of Thrones, Stranger Things, Dune, and these kind of productions. So in the beginning, Sound Particles was originally created by me, a single developer. Now we have almost 20 developers in the team. We have actually 4 development teams. One of them focus on Sound Particles, our main product. Another one pretty much focus on plugins. Another one working on a product called Explorer, pretty much a database management software for sound with some cloud features. And also we are working on our own binaural technology. That's another team. Some additional context, we pretty much use C++ to everything. Version 20, we create things for Mac and Windows. We have some applications that are standalone, some have plugins. And this is pretty much the initial context of Sound Particles. And let's talk about all the mistakes and the pains that we have as growing. So the first version of the team, it was a single developer. And having a single developer, okay, it's great. Everyone agrees with everything. The same coding style, the same decisions, everyone edits the code that was written by themselves. It's a perfect world. Also, at that time, it was just a set of Git repos, no tracker for issues, no building system. The initial version of Sound Particles was only for Mac. And yeah, it's a nice world, okay, if you are a single developer, but productivity is limited, so we need much more developers to be able to do much more things. And then the pain begins, okay? So it's okay, we start hiring more developers and start hiring testers, and the team starts to grow. So with multiple developers, we start having much more developers. Some of the things that we have been doing at the moment, and we still continue, so we use Scrum, okay, sprints with 2 weeks, daily meetings, retro, review, planning, the usual things. We started using Jira to manage all the work, all the bugs, all the new features that we want to implement. Everything is implemented by using Jira, Bitbucket for code repositories. We used Bamboo to manage builds and make sure that code would compile in both Mac and Windows. So you have a developer, they have an operating system, either Mac, either Windows, but you do a commit and you need to make sure that that code actually is running and compiling in both platforms, because eventually it could compile on that platform of the developer, but not on the other one. Also, we used Confluence to share knowledge between the company, documentation, writing user stories, whatever it needs to be done. We use Confluence to manage that and put that on text. At some point, we start using text trail software to manage human test lists, the lists that you do before releasing the product and during development to make sure that every single feature is actually working as it should. And in the case of sound particles, at some point we almost got 3,000 items that needed to be tested before the release, public release of the software. And also we decided to have some code style guidelines to make sure that all the developers pretty much are on the same boat regarding code styles. In terms of quality assurance, we have at least one person for testing, usually audio professional, with some freestyling testing pretty much. Go there, try to break everything and see if it's still working or not. And is this person that actually closes things on Jira. So on Jira, what we do is pretty much we have the list with the to-do, okay? Everything is there on to-do, on the sprint, in progress, on hold. When the developer finishes implementing things or fixing the bug or whatever, goes to the finishes. And then the Q&A starts from there, starts reviewing those things, either a bug that was corrected or a new feature, eventually pending review if there is anything holding back that issue, and then closed, and this is the quality assurance that defines that, yes, this feature is closed. So pretty much everything that we're doing. Regarding automated tests, well, you know the usual excuses. Well, we need to move fast. Yes, we need to release the product as soon as possible. I remember at some point talking to developers and say, okay, but to add automated tests, what would be the impact? And the developer told me, no, we need 90% to write tests and then 10% to write real code. And I asked myself, okay, so you are saying that I need to hire 10 developers to do the work of one. And at that time, we decided not to have automated tests because, you have to release and you are in a hurry. And oh my God, it was a big mistake, as you can imagine. So especially on the software like sound particles, highly complex with almost 1,000 files of code. So not having automated tests was a very big problem and mistake, as you can imagine.
So as Nuno pointed out, this lack of testing culture was a big problem for us. So we did some research about the frameworks that we could use. So we opted for two, Google Test and Catch 2. So our solution was always to use Catch 2 because it was too easy to implement. So the problem without having automated tests that were a huge number of bugs were missed. Okay, developers come with new features that broke previous features. We didn't have regression. We didn't have quality assurance regarding the code being developed. So everyone makes code, nobody tests it. So it was a nightmare. So yeah, we decided to make a pause, okay? And then we have a 2-month stop just to bring this kind of testing culture to our developers. So.
Yeah, pretty much essentially was, okay, everyone stops the development. We need to make sure that we have tests. So it was one of the things, yes, it needs to be done. So let's do it, and we start having automated tests.
So that brings us to development team 2.0. So we bring automated tests to our culture. So among different sites, we opt for Catch 2 because it was easy to use, very easy for developers to incorporate in their code. So a huge effort was made during 2 months to bring thousands of tests to our developed branch. We create a set of bamboo tasks to run tests every night. So It was not fast, okay? But at least we had tests. We tried other things because it became apparent that doing tests using Catch2, it only tests the engine, the render engine, but we have a UI. So we tried to test UI, but we have a problem here because we are targeting both platforms, Windows and Mac. We don't have the native framework for each of them, so we have Views, but in the case of Views, we only use the window abstraction. We have our own UI hierarchy, so it was very hard to implement something from the ground to automate the UI testing. So we decided to opt for Seculi, that you define the region where you click, the region where you capture, and you try to infer what's written in that region. So it was not good because we have too many false positives. So that's something that we'd opt out later. Again, because we didn't have any kind of coverage at that time, we decided, because many bugs are presented in the engine, we decided to have some kind of monkey testing, so to test all the inputs randomly. So it was also a failure because we have too many false positives, and developers spend their time trying to figure out why the test failed, but it was not a bug, okay? It was some kind of API restriction that we didn't validate.
Yeah, the idea of monkey tests was pretty much simply doing random actions, add track, remove track, add microphone, change this, change that, and try to see if you, in some way, the system would crash or freeze or something like that. And especially the main problem that we have with monkey tests is that at some point you may be doing a lot of crazy things, and it's what's difficult for you to differentiate between the freeze of the system or simply doing the work that we asked them to do. So we had at this time Catch2, Seculi, and this monkey testing that we have implemented, but because of the too much false positives, we end up with time to almost ignoring Seculi and monkey testing and continue only with Catch.
So how do you do testing here? For the containers, helpers, classes, it's very easy. It's just like a unit testing. But the challenge came with testing the render engine because we have audio. So to test audio, we opt to do some kind of comparison testing. So the first approach is to write the test. Okay, we call the render engine. We exported the audio file generated, and you give the audio file to the quality assurance to validate if the panning is right, if everything is okay, giving the input parameters of the test. Then we update the test, and now we compare the generated output with the reference output. So if it lies within the error margin, that's minus 120 dBs, okay, the test succeeds, otherwise it fails. But we didn't have the whole picture, and if you could roll back in time, if anyone could do some kind of presentation about the hurdle of testing audio, it will point to these things here. First one is the math difference between compilers. In the slide is system, it's between compilers. So the sine, cosine on the Xcode compilers, or the Clang compilers, Apple Clang compilers, is different from the Microsoft compiler, okay? Even with Mac, the sine, cosine, or log function in debug mode is different in release mode, okay? So that was a lot of pain. So at the time, we make an effort to not to have two comparison files. So we relied on IPP from Intel, okay, to do some kind of abstraction. So instead of calling the stud cosine function, we will call our own cosine function that we'll call the IPP cosine function. And they pretty much have the same result. The problem was not the individual result because the difference was very small, but the accumulated difference will give us an output that will rely outside the error margin. Another situation was related to the random numbers because we have a lot of random numbers, lots of parameters, and we have to cope with that, we have a file with 4 million, I think, random numbers, right? 4 million. We have 4 million random numbers. Instead of relying on the random number generator, we have always as a reference. The parameters choose a random offset within that reference.
Yeah, especially in case of sound particles, where you use particles, there is a lot of random numbers. You say, okay, I want to generate 10,000 particles. Well, on the test, every time that you generate 10,000 particles, you need to make sure that is exactly as the reference, otherwise it's not going to sound equal. So yes, making sure that the random numbers on the tests were generating the same things, it was also a challenge.
Regarding still the random numbers, the challenge here was when we start doing automated testings, give the API some way to set the seed for each parameter, because we don't want to each running test to have different outputs. So they have always the same seed for each parameter, so we have predictability in the results. Then we came mock-harm. So our solution to use IPP was a problem, a big problem. So we spent almost, I think, 2 weeks writing abstractions for all the heavy computations like convolution, FFT, resampling, and the code that we did to abstract the sine and cosine function didn't work because it was IPP related. So at that time we decided to, okay, we must go to multiple comparison files. So we have a comparison file for Mac, we have a comparison file for Intel, okay, Windows, sorry, and if we need, we have also a comparison file for Mac ARM, but at the moment because our pipeline is only Mac ARM, we don't need that. It also became evident that without a coverage tool, it was very hard to write tests. So we brought to the pipeline some kind of mechanism to make it easier for developers to run coverage, and to, when writing tests, always make sure that the tests cover all the codes. Okay.
Okay, so some of the pains, yes, now we have automated tests, yeah, but there is still some pains. The first pain is that, okay, during the night the test will fail, but the bad news is that the bad code is already on the development. Okay, yes, you can try to unroll it and all of those things, but the part of the problem was there. And then it's something that I usually call was not me. Okay, so pretty much imagine this scenario. This happens a lot of times. You start the day and during the night you find out there is 40 tests that have failed, okay? And we, during the daily meeting, says, okay, people, there is 40 tests that failed during the night. We need to fix it. Then what would happen is that usually 2 or 3 developers, you know, the most responsible ones, will lose like 30 minutes each person just to find out if, did I did anything wrong? And then you go there and check the code and the test. And then after half an hour, each one of these good developers find out that, okay, it's not their code. So great. The problem is that most of the times the guilty developer is not even on that team. It's someone from another team that make a change on something that is used by both projects, both teams, and then someone from product B make a change on a library that is used by product A. Product A stops to fail. You tell everyone there is a problem in the test of product A, and the developer says, okay, I'm from product B. It was not me. Okay, so yeah. What we believe would happen is that actually this failed test will live long, because the next day, okay, the test will still failing because no developer have done anything to fix them. And that day, probably they have new tests that are failing because of new commits. So yeah, we have tests, we have automated tests, and we felt the need of a blaming system, not to be a jerk, okay, but pretty much as a productivity. Because if you know exactly which person actually is doing the bad things, instead of having these developers losing time that they don't need to lose, okay, and make sure that the person that actually makes the mistake knows about that.
So with more products under development, we start sharing code between products. It was a necessity. So the problems also start because now to have multiple projects sharing codes, we should set up a multiple repo approach. So that was something at the moment it was the right step to do. It was the common practice. It was easy to put in practice. It was something that developers were already used to. We opt to use the Git flow branching model. So we create a feature branch. Developers will commit to the feature branch. Then they will merge that feature branch to the branch develop. That was a problem because every developer had permissions to merge to develop. Okay, and initially, it was not broken so many times, but at the end, branch develop was broken 2 or 3 times per day. So it was a huge issue. So tests were run once per day at night, okay? Installs were generated every day, also at night. And releases were generated manually. So we have a bunch of scripts to do that. So more code, more developers, more problems. So build times take up to 2 hours. That was pretty much the standard here. So if anyone make a commit to one of the repos that's in the base repo, it will take 2 hours to build everything. The branch develop is broken too many times. We had the necessity to lock down our continuous integration pipeline that was running locally between 6 p.m. and 6 a.m. So just to run the tests and generate installers. And so this was a huge issue for developers because most developers like to work at night. Okay, so they didn't had permissions to commit at that time. So the tests were executed at night. The problem that the failing tests were already in branch development. So the damage was already done. If you want to add new products, all the dependency management was made by hand through Bamboo. So we didn't have any kind of automatic dependency management. And Bamboo starting to be slow. So interacting with Bamboo, just a single click took 20 seconds, average 20 seconds just to navigate across the pages. And the second problem with Bamboo, it was running local, so no remote feedback. If any problem emerged, we should go to the office, okay, and try to see in the logs what happened, so that's not product. So the problem here was this kind of, if you need to change, we thought about that, and the multi-repo was not helping us here, because to create a release or hotfix was very error-prone because you must go to each single repository and place the head in the right place. Also, after publishing the release or the hotfix, if you want to going back and recreate a previous hotfix or release, it's very, very hard because you must go to 10 repositories and place the head in the right place. We didn't have scripts for that. Another major issue is the atomicity of the feature commits, because when I'm doing some kind of feature, I'm touching in the repo A, B, C, but now I have 3 different repos. So if I manage to commit in repo A and repo C, but when I make a commit in repo B, I have a conflict, okay, I don't have a correlated timeline between the feature and the commits. It's a nightmare. Because we wanted to implement a pull request workflow, but it was impossible with very hard. I don't like to use the word impossible, but it's very hard to do that with a multi-repo approach. So also we have the problem that all our products have different release cycles. So it's very hard to manage that in a multi-repo approach.
Okay, so essentially we decide, what about monorepo? And okay, it seems almost like a taboo talking about a monorepo because everyone says, no, we should have a Git for this, a Git repository for that. And someone said, let's think about having one for everyone, for everything, and everyone looks at you. Are you on the beginning of school or something? Did not learn that you use different Git repositories for each things? But then we find out that Google and Facebook and others were doing the same thing. So, okay, let's think about this.
So we did some research about that, and we found that Google, Facebook, Netflix, that's kind of a hybrid system, but it was not something so stupid at first place. So we embraced the monorepo. So we started creating the single repository for all of our projects. Some exceptions, maintenance code or tools that live outside some tools that live outside the monorepo, but other tools like lang format, even juice modules live inside the monorepo. So when you go back in time, you don't face the issue. I'm trying to compile, but this juice version doesn't allow me to compile this. So what were we able to solve with going forward to monorepo? So first, we get rid of management overhead. We have a single source of truth at our monorepo, a single history timeline. We have atomic cross-cutting changes, so we can have a feature commit. Okay, it's atomic. So if I want to check what was made to implement that feature, I just go to that commit and see all the changes. We get rid of silos. That's something that nobody talks about, but if we have multi-repos, you want to have a standardized way of formatting your code, a unique lang format, a unique lang type, and other things that should be common across all projects. Now we have only a repo. It's very easy to do that. We don't have a dependency hell because it's just a monorepo. If we want to go back in time and recreate something, just git check out the tag we want to recreate, okay? It's refactor friendly because we have a large legacy code base from Sun Particle's first version. It's very hard to make changes when you have a multi-repo approach, okay? Because you think you didn't broke something that you broke, okay? So with a single repository, it's very easy to, for example, change a class, changing the resampling class, changing the convolution class, etc. It's very easy to do that. And the most important feature of the monorepo is continuous integration friendly, so we can embrace it through pull request workflow. So the second problem was Bamboo being local, and we have a set of requirements that Bamboo didn't meet, okay? So the first requirement was able to compile for macOS and Windows, okay? The second requirement that's common, I think, in this industry, we have a a large file system repository, okay, 20 gigabytes or more. And at the moment, I think it's 30 gigabytes of data of audio samples, okay, you want to test.
Yeah, pretty much testing material, the ground truth, and all of those things.
We wanted to lock the branch develops, so no developers can commit to that branch. Only the continuous integration service will do that. We want to follow a pull request model, okay? We want to have every pull request to be evaluated and submit for review, human review if all checks succeed, okay? We want to have some kind of automatic dependency management so we can bring new projects to the monorepo without changing anything. Have the concept of code ownership that Git has, so each module will have a set of persons that are responsible to curate that module. So we want also to minimize the LFS operations because with a repository so big like that, we don't want to pull every time we are evaluating a pull request. It will take an eternity. We want to have a pipeline that's always available for 24 hours per day, 7 days per week. Easy to add new checks if we need to, okay, and easy to scale. So we did some research 1 year ago in the market. We look at Travis, Circle CI, and many others. First problem, we want to target both platforms, okay, macOS and Windows, and at that time, pretty much nobody supported macOS. Okay, that's all, the first limitation. The second one was related to LFS because we have a huge repository, and when you pick up the calculator and you make the math, how many dollars will cost you to move all these kind of repositories when you should go check out just to run the pull request. It was forbidden cost. So in the lack of alternatives, we decide to build our own continuous integration service. Okay. So when we put this service in place the first time, the accept ratio was 0. So the developers kindly name this as the gatekeeper you should not pass, because none of the pull requests passed it, okay? It was a very hard moment. He's doing this job. 2 or 3 days, I think, after 3 days, after the first pull request passed it, okay? So what we have done here, we have a look at the alternatives in the market. The solution was heavily inspired in the Bazel from Google. I don't know, so it's Bazel, Bazel. We have each module slash project slash plugin as a build YAML file that specifies the dependencies, okay, specifies the artifacts that are generated. So we can have a project that generates a binary for tests, a plugin, or even a helper application, etc. So we have also inside this file, if the entries, if this project generates an installer, if it generates an installer, how many flavors, because for example, in this example here, we have space control, we have 4 flavors that are triggered by a macro, so we can do that, and we have automatic installer generation. So based on the dependencies, we have some kind of code behind in the service that creates a dependency graph, okay? And because now we have a dependency graph, we have a parallel compilation of modules. So that was a huge improvement. So also, we only need to compile what was affected by the pull request. We don't need to compile everything, okay? New projects and all modules or libraries can be added without any configurations. Just put a folder with a build YAML file, just commit, okay, everything works. It scales automatically by adding pairs because we are tying both machines, so each pair has the capacity of evaluating a pull request. If I want to have 3 pull requests in parallel, I need 6 machines. If I want to have 4, I need 8 machines, etc. It's available everywhere because we have put a kind of dashboard on top of the service. Okay, it's integrated with Bitbucket. We have a single sign-on mechanism and allows developers and everybody to monitoring the pull request when he is submitted. So the new workflow for developers was pretty much simpler because developers now create a branch, okay, they make a pull request. The pull request is evaluated by the pipeline. It checks if, for example, there is any deviation in the styling guide using Clang format. It checks if you are committing binary content outside the Git LFS storage. It was a problem with us because new files, developers forgot to add that to the LFS, and it will appear in the Git version control. Testing for if the code builds, okay, in both platforms, and then if the code builds, if passes all the checks, then the final step is to run the test and check if the pull request passes the checks. If everything is okay, the code goes to review. Because we have the concept of code owners, we already notify developers that are responsible for the touch models to, okay, you have here a pull request that passes everything, it's green, so have a look at it. If everything is okay, after 2 approvals, you can merge that to develop, okay? And that's the current workflow we have now. So everything is implemented in Python because we are targeting both platforms. So just a snippet of how we're doing our checks. So each check is a self-contained Python script that receives as a single argument all the information related to the pull request. So the number of the pull request, the files that were added, deleted, or modified, the dependency graph of that pull request. So every information that the script can use to infer if everything is okay. At the start, we had a Clang tidy check, but we opt to remove that because Clang tidy was so slow that okay, it was not something that we could add to the pipeline. So here's a representation of our dashboard. So every developer using their Bitbucket account can connect to the dashboard and see the state of the pipeline, what's the size of the queue. I think at one moment we have 25 pull requests in queue. That was, I think, a record. It can go to the pull request being evaluated and check what's the current status, if it's building, if it's running the test of module A or module B, etc. So, in summary, was it worth it? It was almost, I think, 2 months of work, right? 2 months of work. Or more. It was a single developer, okay. It was a huge runtime improvement, despite having more code to build and more test suites. So to give you some numbers, the compile time was 6 times faster, from 3 hours to 30 minutes. Now it's 60 minutes because we are kind of building a universal binary for Apple, so it's 2 times, okay. The full test execution, running all the tests of our code base is 2 times faster because you can do that in parallel now. So from 4 hours to 2 hours, we have no lockdowns, so the pipeline is always available. Most important is the branch develop is always sane, is always ready to deploy, okay? So another feature is that we don't have binary content outside the LFS storage, okay? We have Clang format enforcement because now the Clang format tools is inside the monorepo. Everybody has the same Clang format binary, okay, with the same configuration file. That means it's the same formatting for everyone, okay? And we are always ready to embrace the continuous delivery. We are not yet there, but it's ready for that. So dashboard is no longer local. It's a huge gain for remote workers. It was, due to the pandemic, it was obvious that was a huge improvement, okay? We have continuous feedback. We can go to the dashboard and see what's going on. Developers can check if their pull request will be evaluated in 5 minutes or in 3 hours, so they can manage their work with that. And they can even discard PRs, pull requests that are in the queue, so if they want to change it, they can do that. So that's something that was a huge gain, that it was not obvious at when we starting our continuous integration pipeline, was the generation for installs for custom branches. For example, imagine quality assurance say that I think you should explore algorithm B. It will give you better results. So we can create a branch, do some kind of experiment, generate an installer for that branch. That was something that we were unable to do before. So the problem with all that is now senior developers spend 30% of their time doing code review. I will be honest, I hate to do code review.
But it's the price to pay.
Yes, that's a price to pay. That's why I resist so many a long time not to do that, because no, I will not be a developer now. I will spend my time doing code reviews. So where do we stand today? So now, due to this kind of custom pipeline service we build, now we have tools for automating everything, build system, tools for automating can go running sanitizer. So if you want to build using address sanitizer, thread sanitizer is very easy, okay? We have a kind of alias. We are using Ninja. So these tools are so easy to use that some developers that were using Windows now are coming to Mac just to use the tools. So we can run sanitizer, we can run coverage, okay, for the code. We can run from the command line tests in parallel, okay. We have always the test feedback on each pull request. Now, because it's a monorepo and some of the tools are already inside the monorepo, it's very easy to set up the workspace environment. Easy, not fast, okay? It's a monorepo, so if a new developer is hired, so okay, you can spend your morning just git clone. Now you can go make a coffee break of 2 hours, okay? And then come back, and okay, your workspace is ready to start. So we have a better guideline enforcement feedback because we have reviewers, so they always try to match the code with our guidelines. In terms of software quality, now we can make some kind of cross-project refactoring without breaking things. That's very important when you have a large legacy code base.
Yeah, essentially, if you need to make a change in a library that you know that a lot of products are using them, and even if you don't know exactly which products are using, you know that, okay, if the pull request passes all the tests, it's sure that everything is as it should. Yeah.
So we have a better code that's kind of
Yeah, and actually the review, it's one of the things that we were talking yesterday, is that sometimes it's not about having that not well-written code in one place, is that that not well-written code actually starts to reproduce. And a developer says, oh, I like to use this and copy-paste, and at some point there is that not well-written code everywhere.
Sometimes our coworkers find that we are very picky, but the problem is that if you put some code in your code base, a new developer comes, say, okay, that's how you do things, so just copy paste, and the problem escalates. So it's so we have the concept of code ownership. So now everybody knows which models you are responsible for, and we have a blame system that we'll never use, because at the moment we run all the tests on all the tests that are required, that are affected by the pull request are run in each pull request. So every time we have a
system that
it doesn't it's never exercised. Okay. So we have no accumulation of failing tests, because now if your pull request fails the check test script, so okay, it will not be merged to develop. So we always have something. Our develop is always 100% green.
Yeah. Some other things, just to finish that, I think it's also interesting. One of the things that we do at Sound Particles is to have a lot of training. So on the beginning, initially, we had one session, like 1 hour, an hour and a half once a week, to talk about software development or some kind of training that we felt necessary. But at some point, we change for a different format. So now we do, if it goes well, 4 trainings a week, each training like 15 minutes, 20 minutes after the daily meeting, and pretty much to fine-tune things. Senior developer that is seeing too much people doing the same error, and okay, let's talk about this, or okay, let's talk about Unicode because the junior developers are not understanding very well how is Unicode. And also we have the Q&A doing some training and say, okay, let me tell you how can you test this in Pro Tools or in Logic or whatever. Or let's talk about the new audio technology out there. Let's talk about wave field synthesis, just for everyone to know. So we decided to do short training sessions, but several times a week. Sometimes it's simply someone say, okay, there is this video from CPPCon or whatever. I think that every developer should see this. The other thing is that although we use Scrum and continue to use, sometimes Scrum focuses too much on the short time. It's pretty much what are you going to do during the next 2 weeks? And you do that. And then what is the next 2 weeks? And sometimes I felt that there was a need of thinking a little longer. And so we started using OKRs. Pretty much you define what are the goals for the company, what are the key results, the metrics to achieve them, and then you do the same thing for the teams, and then you do the same thing for each person. And right from the first quarter, one of the things that actually was born from using OKRs was test coverage, because we have been talking about test coverage for more than 1 year, okay, but on every sprint you're simply, no, now we need to do this. So we said, okay, OKRs, what do you want to accomplish this quarter? And people say test coverage. And after, I think it was 3 weeks after the beginning of OKRs, we had test coverage. So yeah, it was an interesting. And also OKRs, especially the personal OKRs, it's important for people to get this self-improvement. People say, okay, this quarter I want to read this book or watch 10 videos about how the developers conference or CPPCon or something. So yeah, it's something that I think it's interesting. Things that we don't have but should.
Automated tests, because it's a huge effort. It's not in an OKR, so but it's really a huge effort to automated UI testing, because we must bring some kind of accessibility feature or identifiers to the components, so we can write code to assess the user interface. Lack of performance tests. For example, we don't know if some of our heavy computations are slower or faster. So some kind of analytics for compile time as the code changes, because now we are embracing more meta-programming, so lots of templates, and they will affect compile time. Lots of things that now are const expression, so we would like to have some kind of metric. And then, because we are testing everything, although it's only 30 minutes to 1 hour, so we would like to have some kind of automatic text selection based on the pull request code that was changed or deleted or added, okay? And also we need to have some kind of dynamic test input size, because reducing the number of samples we are trying to render, because maybe during the pull request we don't need to check for 5 seconds of audio, maybe only 1/10 of a second will be enough. So that things that we don't have and they will like.
Yeah. So essentially, this is what we wanted to share with others. I would love in the future to see the same thing for other companies and other organizations, and to know more about these logistics and operations of which everyone is using. And feel free to make your questions. Thank you.